Yeah, I think I'll go without the mic. Is that okay? Can you hear me okay? Okay. So I threw the bye Tina Keller on at the end because I thought it was pleasant. I don't really need it. So let me just start by mentioning a couple of things. I have encountered this question a couple of times, and I do encounter it when I teach the astronomy course at USD. And I'll tell you a little story that happened to me probably one of the first times I taught it. It was probably more than a dozen years ago. And at the end of the semester, we do the talk that's actually an expanded version of what I'm doing today. But it sort of ends up, the class ends up with how did things start? And so this is obviously where did the universe come from? And it can be a very controversial topic. And so on that particular class day, a student, a young person who I had never seen before, walks into the classroom and sits down in front. And the immediate thought that pops into my head is this is someone who is going to get up and challenge me the minute I start talking about the origins of the universe. Well, I don't know what happened to the kid. He sat there perfectly quiet and attentive the whole class time. He didn't say a word. He didn't 5 minutes into the thing go, oops, wrong time, wrong class. So it was one of those things where I was expecting something that never quite happened. So I don't quite know what the point of that story is. But I do encounter, and I am very sensitive to the fact that some of the things we talk about can be a little bit, world-shattering to some of the people to whom I am telling the story. My second involvement, or the one I actually didn't remember at all until Gary pointed it out to me when I told him I was doing this, was something that actually led me to receiving the title of honorary theologian for Sanford Lab. And it had to do with a question that was asked to me in a panel discussion with the Governor Rounds, and Barry's laughing because I remember he was pretty annoyed with a few other things that happened during that talk. But one of the questions was, when the physicists are trying to answer the questions of, the universe and where does that leave God, I thought I gave a pretty good answer that sort of left it up to the individual, that the scientist can only take you so far, but at some point in time, there comes a point where you decide what you believe. And that's where faith comes in. And that's the difference between science and faith. And I actually thought that was a pretty reasonable answer, and I thought a lot of other people did. But one person on the panel didn't, and responded quite vocally to that comment. I won't mention who that was, but it was a rather fun experiment. So here's what I'd like to do today. I will talk about the universe, and I think there are some questions that I would like to answer for you. And the nice thing about giving a talk about the universe is there's a lot of really cool pictures out there. And so I just threw these pictures in these slides so you're doing more than just simply looking at a bunch of words on a screen. But what I'd like to do is sort of take you through a story, because if we're going to try and understand the universe and perhaps where it came from, we need to know a little bit about it. And so I'm going to answer the question of how big, and in answering the question of how big, I'm going to take you through the process of how we can get to the point where we can say, this is how big the universe is. This is how far away we think sort of that last part of it may be. I'm going to try and answer the question of how old, because if we're going to talk about, how things started, we need to know how far back we need to look. And then I'm going to talk a little bit about beginnings. I mean, what do we think happened at the start? And what can we say from the evidence that we see and the experiments, and maybe not experiments, but measurements that we've made? What can we say about how things started? And then I think it might be worth having a conversation about the end. What do we think will happen at the end? Tomorrow? 10 years from now? Well into the future that we don't have to worry about things? I'll tell one more story because time is important. Hans Bethe, who worked out the way energy is produced inside the sun, and was telling the story about figuring out sort of the fusion and understanding how much, energy the sun will have, how much fuel it has left to burn, and when it will finally run out of fuel. And the answer was like 4.5 billion years. And so he said one person at the conference raised his hand and essentially said, is it 4.5, did you say million or billion? And he said billion, and the questioner had said, "Ooh, that's a relief," because as if 4.5 million would be way too short. And so I like that stuff. But so let me start by answering the question, how big? And what I will do is take you through sort of the measuring process that astronomers do to figure out how far away things are. And so it's very easy for us, if I were to give you a task, although I think Jake's probably the only one who can assign questions. If I were to give you a task and say, one of the things you need to do before you leave today is tell me what the diameter of your tables are, you could probably figure out a way to do that. I mean, some of you might say, we'll go see if the bartender has a ruler of some type and we'll put it on the table and figure out that it's, 5 feet across. And some of you might get clever and say, let's design our own measurement system and we'll use Pastor Miller's hand as our unit. We'll decide that there are 17 of those hands across the table. But you've devised a way of measuring, and it's actually pretty easy because you can develop your standard and you can actually put that standard on the table and you can figure out how that table compares to your standard. Astronomers have a little bit tougher time because I really don't have a tape measure that will stretch from the Earth to Mars, or from the Earth to the Sun, or clearly from the Earth to the nearest star. I just don't have that. I don't think we ever will. And so what we need to do is we need to figure out clever ways to make those measurements that are reliable, right? I can't just come up with a number and say it's 1 billion miles to the Sun, because that's not science. You want to know, how do you know it's 1 billion miles to the Sun? So what astronomers do is they come up with some techniques and tools that they can use to measure these types of distances. Now, I'm reminded I should stop here for just a second. I am assuming that a lot of the sciencey things I say are things that you are familiar with. But if I say something that you just simply don't understand, raise your hand and ask me to clarify. I'll be happy to do that. And so, we physicists sometimes just get, enamored with our equations and numbers, and we forget about really explaining things. So if I've said something that isn't clear, or you'd like a better explanation, please let me know. So let me start first by the first word that I have up there is parallax. And so the very first thing that we need to do is come up with that first step out to measure the distances. And sort of the very first thing we need to do that is to figure out sort of the scale of the solar system. So this was a really important challenge. How do we figure out how far away we are from the sun? Now, how many of you know the sun's at the middle of the solar system and everything goes around? Good. Okay. There was actually, when that model was proposed, there is some pretty significant evidence that should be observable if the sun is actually at the center and the Earth moves. And the trouble is the evidence is really hard to observe. And so the idea was proposed well before anyone would really ever be able to say, look, we have the smoking gun that proves we're right. Part of the reason for putting the sun at the center is it allowed a really clever mathematician, any clever mathematician, to be able to calculate relative distances. So that with the sun at the center and observing the motion of the planets, I could say if the Earth is 1 standard unit away from the sun, we can use geometry to figure out that Venus is 7/10 of that distance, and Mars is, God, I've forgotten, like 2.4. I'll look at Tim's the one in here that I'm worried about. and so that was really good. And then with, you know, with actually modern day equipment, we can bounce light radio waves off of Venus and measure the transit time. And we can measure that scale to a very, very high degree of accuracy. Okay, so we have the solar system well defined in terms of the size. That's a measurement that we're really quite comfortable with. The distance from, let's say, the Earth to the Sun. It's not constant, it varies as it moves around, but we know it, you know, we're very, very comfortable with that measurement. Okay. So now here's what happens. As the Earth moves around the Sun, and Howard's in front, so I'll use Howard. If it's July right here, and I'm looking at Howard, Howard is lining up with the background over there with these guys in the corner. Okay, this is July. And now I move around the Sun, and I'm over here in January. And now Howard is lining up with those guys back over there. And so one way of actually verifying that the Earth is moving around the Sun is being able to see some of these shifts. Now, if I pick on David, and I line up David in, where was this? July. Right. He lines up with those yellow guy, that guy in the yellow shirt back there. And if I come over here and line him up in January, he lines up, okay, I'll lean over just a little bit more. He lines up with Beard. Now, the gap between these two guys here and these two guys here is actually much smaller. And so the farther something is away, the smaller that shift. And so what we can do using geometry is if I know how far I am from here to here, and I can measure that angle between these two positions, I can figure out how far away Howard is from me and how far away David is from me. And that's simple geometry, and we can make those measurements reasonably well. Now, the problem with those measurements is, like anything you do, if you've ever read a ruler, there's lines on the ruler, and it's easy when everything's right on the line, but it's not so easy when something's in between the lines, because then you have to make an estimation. And so there's a limit to how closely we can measure those angles. How many degrees in a circle? Degrees. Yes, okay. Do you know what degrees? If you know, you have yards into feet and feet into inches, I can break degrees up into smaller things. 60 minutes in a degree, 60 seconds in a minute. And so roughly in one circle, there are 60 times 60 times 360, a little bit more than 1 million of those little seconds in a circle. We can measure an angle shift for a star that is down to about 1/100th of that from just a decent ground-based telescope. Now here's what astronomers do. They like math, but they don't like to spend a lot of time doing math. So they invented a new unit of measurement based on this geometry, that if I just take 1 over that angle in seconds of an arc, in those units of seconds, if I take 1 over that, what I will get is I will get the distance to the star in a new unit of measurement called a parsec. So a parsec is a parsec. It's short for parallax arc second. That's what it is. It's a parsec. Okay. It's 3.26 light years, and a light year is the distance light will travel in a year. So if you want to do the calculation, there are roughly, this is a fun number to remember, there are roughly pi times 10 to the 7th seconds in a year, and light travels at about 3 times 10 to the 8th meters per second.
That
so,
is fun.
So it's roughly, you've got about roughly 9 followed by 15 zeros meters in a light year. And so it's a really, really big number, but astronomers like it because you measure the angle, you put 1 over that, you get the distance. Here's the problem. Because you can only measure those angles down to about 0.01 arc seconds, it limits the distance of how far you can see. 1 over 0.01 gives us 100, right? It gives us 100 sort of for that outer distance. And then it also introduces some error. Because if you can only measure down to 0.01, you don't know if 0.25 is 0.24 or 0.2, you know, it adds some error into the measurement. And so this first step gives you some error. But that's okay. We can make really good measurements, and we have a way of measuring distance out farther. Now what you do is you say, well, now I can't measure those angles anymore, so I need to go out farther yet. And you start to look at the stars that you can see, and you start to measure properties of them. And here's what you find out. You find out that stars that have a particular color sort of have a reasonable, have a similar brightness. And so what you do is you make a graph. I've got to push the right button. You make a graph like this. It's called a Hertzsprung-Russell diagram. And what you do is you just simply plot stars by color and brightness. And so what you have to do to create this is you have to use stars that you know the distance to. So you have to start with close stars, because you don't know how bright they really are until you know how far away they are, right? A flashlight looks really bright if I come and stick it in your face, but it's not very bright if I stick it way over in the corner of the room. So we need to know how far away the stars are. And you can do that for those stars that are within 100 parsecs. And what you find out is these stars, color and brightness, most of these stars fall on this little path called the main sequence. So here's what this lets you do. You can look at a star now that you don't know how far away it is. And you see this star and you can measure its actual brightness, okay? How bright it looks to you. Okay? Its apparent brightness. How bright does it look? And then you can measure its color. And I won't go into the details of measuring the color, but you can measure the color and you can put it on this little chart. And once you put it on this little chart, you know how bright it really is. And if you know how bright it should be, and how bright it actually looks, you can tell how far away the star actually is, because the dimmer it is, the farther away it must be. So this gives us another step out, and astronomers call this spectroscopic parallax. And it works really well until you get to the point where you can no longer begin to see individual stars. And so now you start to look for other things that astronomers call standard candles. And standard candles is just a fancy way of saying something that we know how bright it would be if we knew how far away it was. And so there are a lot of things that can be standard candles. There are stars that vary in brightness, and we find out that the period, how quickly they go from bright to dim and back to bright again, is related to how bright they are. We find certain type of supernovae that their brightness is directly related to the type of supernova you look at. And then you can actually use the overall brightness of galaxies to help you determine their distance. There's a relationship between the brightness of galaxies and some of the other properties. So we begin to look for these additional things that will allow us to move farther out. And a good standard candle is something that's really bright, so you can see it a long way away, and is something that truly is standard, that always is the same brightness whenever you see it. And so what that allows us to do is that actually allows us to start to measure the distances to galaxies. So we live in a galaxy called the Milky Way, and actually one of the very big questions in astronomy was, are these fuzzy things that we see in the sky, they were called the spiral nebulae, are they part of our galaxy? Is the Milky Way sort of the universe? Or are these spiral things outside of the galaxy? And Edwin Hubble was one of the first people who recognized a variable star in the Andromeda galaxy and was able to show that this thing is farther away than the size of the galaxy. So he showed that this Andromeda, this spiral nebula, the constellation Andromeda, which we now call the Andromeda galaxy, is outside of the Milky Way. It's another sort of island universe, if you will. Now, once Hubble did that, he started to look at all the other spiral nebulae, and he noticed something really pretty interesting. That these galaxies now actually appear to be moving away from us. So what does that mean, and how could he tell that? I did put an equation on here. I just couldn't help myself. But let me talk to you a little bit about, and here's a picture of Hubble looking through I think it's the Hooker telescope. But let me talk to you a little bit about redshift. How many of you have ever stood by a train track, had a train go by, and you've heard that distinctive change in pitch of the train? If I had a better voice, I'd do it for you. It's high when it comes toward you, and then you hear it drop as it moves away. And that's a physics effect called the Doppler effect. It happens for anything that's a wave. It happens for sound. It happens for light. And for light, if something is moving toward you, its wavelengths will be squashed a little bit, and it will look bluer. And if something is moving away from you, its wavelength will be stretched a little bit, and it will look redder. It's sort of the basis of a radar detector. By bouncing the radar off of your car and looking how much the wavelength has changed, they can figure out how fast you're going. And so Hubble used the redshift. And does this make sense, or should I explain it a little bit more?
It does.
Makes perfect sense. Okay. He used the redshift to figure out how fast these galaxies were moving. And what he found was this very, very regular relationship between how far away the galaxies were. So he had some independent measurement of figuring out their distance, some standard candle in that galaxy, and the redshift. And the farther away they were, the faster they were moving. And he actually came up with a nice little equation for that, where the speed of the galaxy is equal to Hubble's constant times the distance. Now, Hubble's constant is one of these things that astronomers really are working hard to figure out. And you can watch sort of the progression of Hubble's constant over the year. And there are some really important sort of conclusions one can draw from Hubble's constant. But there are a number of different ways to find it. And so, some of the best estimates you'll see right now will be about, 74 kilometers per second per megaparsec. Okay, so that's speed over distance. And, another way of measuring it will get you about 67 kilometers per second per megaparsec. Now, we need to think about what this means for just a second. These galaxies are moving away from each other, right? Everywhere we look, we see galaxies moving away from us. And it doesn't really seem to matter in which way we look. Everything sort of looks the same. Now, if you're standing somewhere, I know I'm not in the middle of this crowd, right? Because I look this way and I see a lot of people, and I look this way and I don't see anybody. If I come in here and I look this way and I see, 10 people, and I look this way and I see 10 people, and I look that way and I see 8 people, and I look this way and I see 8 people, what's my conclusion?
You're in the middle.
I'm in the middle. So this was actually, remember that horrible moment early in humanity's history when they had to move the Earth away from the center? Now we're back in the middle. That's pretty cool. We're back in the middle. Don't get too excited. But, so everything's moving away from us. Are we at the center of the expansion? Are we at the start? Is the universe expanding? Before I answer that question, let me do one little game with this Hubble constant. If you remember from your science class, you did something called dimensional analysis, where you would cancel things out. So kilometers is a measure of distance, right? And megaparsecs, remember parsecs were a distance, so mega is just 1,000,000 parsecs. So what I'm doing is I'm dividing a distance by a distance, and that cancels out, right? And then I'm left with seconds in the denominator. And so if I take 1 over seconds, I get seconds, right? So the dimensions of the Hubble constant are 1 over time. Gary's confused.
But we're both confused, so it's okay.
All that you need to know is that the units of the Hubble constant is 1 over time. And if I take 1 over the Hubble constant, I get time. if I take 1 over the Hubble constant, doing the appropriate unit conversions, which I didn't, which I was kind enough not to put on here, we get 13.7 billion years. So, you know, what is that sort of representing?
So, I'm sorry, so Tina, are you saying Hubble's constant is about 13.7 billion?
I'm saying 1 over
1 over
Hubble's
Hubble's
constant
okay.
is 13.7 billion years. I can do the math for you, but oh, I can't help myself. It's really easy. You take 1,000, you take a kilometer, and then you divide by the number of kilometers in a megaparsec, which you can all do, right? Because a mega is 1,000,000, so you divide by 1,000,000, and then you divide by 3.26 light years, and then you divide by 9.4 times 10 to the 5th. Anyway, and then you take 1 over that, you get 13.
Tina, this is like putting when it's already been conceded.
Yeah. So, this is how.
That's good.
Yeah, Gary really appreciates that. So, the universe is expanding, right? And so let's just run it in reverse. Let's run it in reverse. Everything's coming back together. Hubble's constant, if we take the age of the universe as 1 over Hubble's constant, we get a value of about 13.6 billion years. So the best scientific evidence right now seems to give the age of the universe at about 13.6 billion years.
Does that presume we've seen the edge of the universe?
That's a really good question. Because there's another way of thinking about, I don't have this slide, but let me answer that question for you. There are a couple of other ways to think about the age of the universe. And initially, you know, and science is an iterative process, right? You make a statement, and I say 13.6 billion years, but you know, remember this is built on a bunch of measurements that are built on increasing levels of uncertainty. And so some of the early problems with this were when you looked at things that you saw in the universe that you knew must be so old based on sort of how you understand stars live and die, and they appear to be older. You know, Hubble's constant has an age of 10 billion years, and you're seeing things that are, you know, 13.5 billion years old. That's a problem, right? That's sort of like when the geologists needed, you know, the age of the Earth was 7,000 years, and geologists needed a few million years to explain process. That's a problem. And so, so another way of thinking about sort of the age of the universe, which also gives you sort of an idea of the size of the universe, is what's the farthest thing we can see? Why is that important? Because light takes time to get from that to us. And so when we look out at some of these things that are really, really far away, we're also looking back in time. So you could think about the farthest object that I can see, if I can measure that distance, and it turns out to be 13.6 billion light years away from us, then light had to travel, you know, roughly that amount of time to get here. So that gives us another way of thinking about the age of the universe.
So Tina, can I ask a question?
You may.
So I'm bothered by this idea that any way we look, it looks like the universe is expanding away from us.
I'll fix that.
Good, thank you. Because that sounds like an illusion.
I'll fix that.
Okay.
So, you have to read the comic, because it was funny, and so I stuck it in there.
Can you read the caption?
Sure,
Yeah.
sure. So we've got the big scientist
Oh, yeah.
and the little
Okay.
scientist.
Got it.
And the caption says, "There goes Williams again, trying to win support for his little bank theory." Okay, so let's start talking about beginnings. Okay. So the natural thing to think about this, if the universe is expanding, then let's run the film in reverse. And so everything should be coming together. And what we start with is we start with this very, very, very small point, and then everything expands. Now, the balloons, I don't know why I said this now. The balloons down here on the bottom just give you a way of saying, okay, if the surface of the balloon is expanding, when I start here, these dots are very close together, and then as the balloon expands, C and D are much, much farther apart. And so to every spot on the surface of the balloon, when they look this way and they look this way, they see all these dots moving away from each other. Now, here's the tough part. If I ask you where the center of expansion for this balloon is, if I said, think about the point about which this balloon is expanding, where would you say that point is? You'd say the center of the balloon, right?
Yeah.
Okay.
Everywhere is the center close.
Pardon me?
Everywhere is the center.
Well, I mean, if you're thinking about, I squeeze this balloon down into a point, it's expanding from the center of the balloon. Now, I'm going to change your universe for you. You live on the surface of the balloon. And your universe is solely the surface of the balloon. If I ask you, in your universe, where's the center of expansion? Where would it be?
Here.
It would be really nowhere, because the center of expansion isn't in your universe.
Wouldn't it look like where you are on the surface of the balloon?
Where you are on the surface of the balloon will be exactly your perception of everything's moving away from me. And when I look that way, I see the same number of spots moving away from me. And when I look, when I look this way, I see the same number of spots moving away from me, and when I look this way, I see the same number of spots moving away from me. And so the surface of the balloon really has no center of expansion in its universe. That's like us. We are part of this universe that's expanding everywhere. And when you think about the Big Bang, you can't think about it as an explosion and stuff goes flying out into space. You have to think of what's happening as the universe is growing as this expansion happens. And there is no center of expansion really in our universe. Everything looks the same. You need 4 dimensions, actually you need multiple dimensions, and you need to be able to think about, what's that dimension outside of ours, which is why it's a pretty hard concept for a lot of us to understand. Okay. So let me just talk a little bit about this evidence for the Big Bang. We see it through the movement of galaxies. The other question that puzzled astronomers for a long time is there's this nasty little force called gravity that sort of holds things together, right? If I were to pick up Howard's pop can and let go of it, it would fall. And so the question with sort of the structure of the universe is if I put a bunch of stars and galaxies and stuff out there, there's this gravitational force that's pulling them all together. So, how is that stable? They shouldn't be stable. Gravity should be causing the collapse. And so we have this stable universe that what we have is this expansion, which, gravity may be pulling things together, but we still have an expansion. And then the last really important bit of evidence is the cosmic microwave background radiation. And this image right here is just is a map of sort of the leftover energy, what was left over from this very hot universe at the start. This is how it looks as it cools down. It has this very interesting structure to it. It's not smooth at all. It has these ripples. Okay, so let me talk about this cosmic microwave background a little bit. It's heat left over from the Big Bang, and let me just talk a little bit about sort of what this means. Okay, so here's a little more physics for you. All of you sitting in this room are giving off light. I can't see it because I'm not sensitive in the infrared portion of this one. But all of you are giving off light. And if I could measure the light that was coming from you from very, very long wavelengths to very, very short wavelengths, I would get a very distinctive peak. There'd be not, a little bit of radio, a lot of stuff in the infrared. If we turned all the lights off, I'd have to do that so I don't see the reflected light. A lot of stuff in the infrared, not much in the visible, and it would all drop off. And I could tell from where that peak occurs what your body temperature is. And we can do that for stars. When we really looked at the color of those stars earlier, what we were looking at was where most of the light is coming from. If most of the light is coming from the yellow part of the spectrum, the star looks yellow, and if most of it's coming from very short wavelengths like ultraviolet, the star's going to look blue or white. So this idea that the universe should have the same type of curve, and we should be able to measure sort of the temperature of the universe by measuring this radiation, was proposed by this Princeton physicist. And he had suggested we should go out there and look for this particular signature of radiation. At about the same time, at Bell Labs, Penzias and Wilson, Arnold Penzias and Robert Wilson, set out to sort of use this new radio astronomy to measure things about galaxies and the stuff that's out there. And they found this annoying problem. This was after World War II. Radar is now well known. Let's use it to do something useful. Let's use it to measure the stuff we see out there. And their telescope had this really annoying problem to it. No matter where they pointed it, there was this static. There was this noise. And they tried everything, right? They thought it was pigeons. They were out there chasing the pigeons away and cleaning off the pigeon droppings. And it didn't matter. They just kept getting this really annoying signal, regardless of where they pointed it. And finally, the two groups got together, and the Bell Labs guys were like, hey, we found the signature, and maybe what we're seeing is we're seeing sort of the leftover remnants of the Big Bang. So, what do we have then? In the beginning, I borrowed that. So here's what we think. We start, and I want you to pay really close attention to these times. We start very early on in something that we call the Clink era. It's about 10 to the minus 43 seconds. 10 to the minus 43 seconds. These lights are flickering in here at about 120 times a second. That's 10 to the minus 2 seconds, and we can't tell the flicker. 10 to the minus 43 seconds. I mean, that's, this doesn't even begin to describe. At that point, after sort of this starts, what we can say at 10 to the minus 43 seconds is it's really hot. It's like 10 to the 32 Kelvin. It's really, really hot. And at this point, gravity splits off from the other forces that help explain what's happening in the universe. Before this, from 0 to 10 to the minus 43 seconds, we have no idea. In order to have an idea about what happens there, we need to combine quantum mechanics and general relativity. We need a model for quantum gravity, and we just don't have it yet. So this, we don't know. About 10 to the minus 30 seconds. This would be the grand unified theory era. And notice something very unique here, or something I want you to pay attention to. All of a sudden, there's this really big step outward. So it's going up, but there's this very almost horizontal slope here. We begin to separate another force of nature, the strong force, from the electroweak force. And in that process, there's probably a significant release of energy, and the universe gets big really fast. We call that inflation, and we'll come back to that in just a second. About 10 to the minus 19 seconds, we have the electroweak era. And here at about 0.01 seconds, we get into the end of the particle era, where we're beginning to take pure energy light and we're starting to create particles. Particles, antiparticles, they come into existence, all sorts of exotic particles, they go out of existence, they annihilate each other. It's a very busy, it's a very active universe. 10 to the minus 19 seconds. Still pretty short. About a millisecond here, we sort of start to end the particle era, and we're starting to cool down, and we're moving into this region after about 3 minutes of when this started. We're beginning to produce nuclei. So it's cooling down enough that we can begin to take hydrogen, these protons, and begin to form helium. And so now we have a sea of nuclei, hydrogen, helium nuclei. And this continues to cool. And now we're getting to something where we've sort of passed through what makes sense to us, right? A millisecond and about 3 minutes, those are times that make sense to us. Now we're getting to the point here where we're starting to get to times that are too big, and it's really hard to understand, you know, what does 380,000 years mean? And it's now cooling down where we're ready to be able to start forming atoms. And another, billion years later, these atoms are beginning to clump together into a way that we form galaxies. And here we are about 14 billion years later. This stuff right here, if this were drawn to scale, would be compressed down into this very tiny point. What sort of evidence do we have for this? Well, the ratio of hydrogen to helium, about 75% hydrogen to 25% helium, is about what's predicted by the processes that's occurring right here. And many of the other measurements we've made seem to indicate that this is probably what happened. Now, before I get to the endings, I want to talk about a couple of other things. Maybe. Dark matter, dark energy, and both of these are going to sort of affect what happens at the end. Sort of what our ultimate fate is. I think that's an important question. Yeah? You're not nodding, Jake. I don't know. Scared. I am too. So you've all heard about dark matter. I think dark matter is the stuff that's out there, and you'll see graphs like this because what you'd expect when you look at a galaxy is gravity controls their motion, right? The motion of the stars in the galaxy is controlled by gravity. And typically, as you move farther out, you'd expect the speed at which things are moving to start to drop off. And in fact, what you see is you see things staying pretty level. And these particular velocity curves, as they're called, where you're just measuring the orbital velocity as a function of distance from the center, can't be explained by the stuff we can see. So what you do is you propose things that you can't see, and you call it dark, and you call it dark matter. And you do one of two things. You either throw out gravity, or you propose something that you might not be able to see. Physicists have done it before. They did it with the neutrino. They proposed this little thing that they thought they'd never be able to see because they wanted to save conservation of energy. That's a really important idea for physicists. And they eventually found the neutrino, and so there was much rejoicing. And so, dark matter, so there's clearly lots of indirect evidence for it. And one of the really important things these days would be able to sort of demonstrate direct measurement of dark matter. Some of the candidates for dark matter initially, that there's these massive, very dark objects in the halos surrounding galaxies. They were called massive compact halo objects, or MACHOs for short. This is so clever. Astronomers are clever. And so it was probably determined that maybe this is not a possible solution, although people are still considering MACHOs. And then it was proposed that maybe it's some new exotic form of matter would be weakly interacting, that maybe interacts only through the gravitational force or maybe the weak force, And those would be called weakly interacting massive particles, or WIMPs. So you have nachos. And so the problem of dark matter is one that's actually a pretty hot research topic right now, and one that USD is actually involved in. Dark energy, who knows? Here's what we know. You'd expect the expansion of the universe to be slowing down, because gravity wants to pull things together, and in fact it appears to be speeding up. That's a problem. And then the other thing that's really important to understanding sort of what's happening is to recognize that space is curved. And whether space is curved like this, or whether it's flat, or whether it's maybe curved the other way, sort of has an implication of what might happen to the universe. These two pictures down here, this is called an Einstein cross, this is an Einstein ring, and it's an example of how matter, dark or regular, can curve space. What you're seeing here is actually these 4 dots all represent an image of the same background object that's hidden behind this galaxy right here in the middle. And what happens? I'll see if I can do this with my hands. Light from this background object comes out like this, right? And we expect light to travel in a straight line. If there's a massive object in between me and you, that massive object bends space. And so the light follows the curvature of space and comes around like this. Now you, as the observer, expect light to move in a straight line. So here's the light going this way that comes back, and you think it's over there. And here's the light going this way that comes back, and you think it's over there. And so there's 2 images of the same object. And it was first observed with quasars, and it was like, there's these 2 quasars that are identical, over here and over here, and that would just be too much of a problem. So the dark energy, we don't know. Maybe it's some cosmological, some energy contribution of the vacuum that's causing this expansion. We have virtual particles coming in and out of existence. Maybe Einstein was wrong, but sort of the bottom line is, when we look at the expansion of the universe, a slowing expansion would be a curve that comes like this, and an accelerating expansion is one that comes like this. And you know what? We're seeing this, and that's going to be hard to explain. And then the other sort of really interesting thing about sort of the curvature of space is, let me actually jump to the next slide. One of the things that you'd like to be able to understand if space is curved is, if space curves like this, the universe is sort of finite, and we'll probably come back together. If space curves in that saddle-shaped geometry like that, it's infinite. And if space is flat, it's right at the critical value that's just sort of the balance point between the 2. So when astronomers have done experiments, they found it to be almost flat. It's like right at that critical density, which is really, really odd. And your next speaker may actually have something to say about that. But it's actually really pretty, it's like almost right there. It could be 10 times too small or 10 times too big, but it's almost right there, which one might want to explain. And actually, we do have something that explains some of that. There are a couple of things that the Big Bang fails to really explain. When you looked at that picture I had up there, that red and black one, it was bumpy. The Big Bang can't really explain that. Inflation. And what I mean by inflation is that part of the picture where it was going up and then all of a sudden it went out real wide, where the universe got really big really fast. What it does is, okay, so this is the part where I feel like I maybe hit in the weeds, and now I'm asking for you to just bear with me. Space is not empty. Space is actually a pretty busy thing. A vacuum is actually a pretty busy thing. And you have vacuum fluctuations. You have stuff coming in and out of existence all the time. And so what these vacuum fluctuations can happen is you have this little vacuum, this little psh, and if it happens during this period of inflation, you can go from something where you have a fluctuation that's, the size of a nucleus to a fluctuation that suddenly becomes the size of the solar system, which gives you that inflation can explain that bumpiness. It's very uniform, and so the question becomes, how can these two parts of the universe that are very, very far away from each other really be so similar? And so inflation can answer that as well, because prior to the inflation, they were close enough together that light could easily move between those two parts. And then the critical density, why are we so close? Because when you get something that's really big, it looks flat, right? The Earth looks flat when we're on the surface. If you get up away from it, it's round. But big things have an appearance of being flat. And so this rapid inflation can explain why the curvature looks flat. So let me leave with endings, and this is one where I can't really answer the question. There really are 4 possibilities. We might have a universe where the expansion slows and it comes back together, and we end up back sort of where we started. And this actually has a great appeal for people, because what you can see then is you started here, you end here, and the process can essentially repeat itself indefinitely. You could have a flat universe, which means that gradually the universe will continue to expand, but it will slow down and it will take an infinite amount of time to get to where it needs to go. You could have a coasting universe, where the expansion remains relatively constant, but the bottom line is that eventually it will just get colder and darker and farther away from each other. Or you could perhaps have an even worse scenario where you have an accelerating universe, which it might be what current experiments seem to indicate we're living in, where it gets cold and dark